Take a look at our definitions to start. First, we have the word amplitude, represented by a capital A. And this is the maximum displacement from the equilibrium position. And we saw this in the last lesson, but if you think about a spring, let's say this is the normal length of the spring. When a spring is stretched and it's in vibration, and then the spring is compressed in its vibration here. So by identifying the center of the mass here, and then the mass is here when it's stretched, this is our displacement. Well, when it's in vibration, it's going back and forth. It's oscillating. So the max displacement, well, that's really like our delta x in this problem. Okay, but that would be called the amplitude. And the units vary. Because if we're looking at a spring mass system, then the units would be in meters. Okay, and the other amplitude would be here. Well, that's this distance over here. And they should be the same, really. It should be symmetric when it's oscillating in simple harmonic motion. This is also analogous to our pendulum. Okay, here is our maximum amplitude, theta. Here is theta. Okay, the theta value is what amplitude is equal to here. And that would be measured in degrees. This would be in meters. So again, the units vary for amplitude, but the amplitude is the maximum displacement from the equilibrium position. The period is the time it takes to complete an actual cycle. So for example, the time it takes for this pendulum to start here, go through here and back. That's one period. That's another period, and so forth. Same thing with this mass. If the mass starts here, it's going to go vibrate out, come back in, and then come back to here. That's one cycle. Or you could think of it starting here, and you could say that the mass is stretched. You let go, it compresses all the way, and then comes all the way back out. That's one cycle, and that is the period, the time it takes in seconds for that to occur. This symbol here is called tau. It's spelled T-A-U. Finally, the frequency is really like a rate of cycles, or how fast it's cycling. The number of cycles per unit time. And it's usually cycles per second. And when it's in cycles per second, we call that hertz. Hertz, represented by Hz. And the symbol for frequency is this symbol called omega. It looks like a W, but it's more of like a bubbly W. Okay, it's a Greek symbol, and you don't need that middle. Oh, there you go. Alright, but this is the frequency, or the amount of cycles that occur per second. So to relate these, the period and the frequency, which we're going to do in a moment, but take a look physically here. If it took, let's say, 10 seconds to complete a full cycle. Okay, 10 full seconds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's back. That means that the period would be 10 seconds. Now, after 1 second, how much of a cycle does it complete is the question. That's what frequency really is. So it would complete 1/10 of a cycle after a second. So after 1 second, it's like here. After 2, it's here. After 2.5, 3, 4, 5, 6, 7, 7.5, 8, 9, 10 seconds. So after 1 second, it goes through only 1/10 of a cycle. So the frequency would be 1/10 or 0.1. So what we'll notice here is that these are inverses of one another. So next we're going to look at the relationship between the period and the frequency of the simple harmonic motion. And what we'll notice is that they're inversely related to one another. And we'll see this here in the first formula where omega equals 1 over tau. Again, omega being the frequency and tau being the period. So this is just verifying what we said a moment ago. Another way to write this is that omega equals tau to the -1. Again, meaning the inverse. And you'll see that key on your calculator, x to the -1, you can use to find the inverse, or just simply do 1 divided by that number. The next two formulas are where it's really important here. And we're going to take a look at the period of a mass spring system and a simple pendulum and see that they're analogous to one another. So all of the laws that pertain to a mass spring system are analogous to those of a pendulum, but with different parameters. So where in a mass spring system we're looking at the mass and the spring constant, with a pendulum we're looking at the length of the cord and the gravitational constant on the planet. So the denominators are pretty much both constants, whereas these numbers in the numerators here are variables based on the actual object itself. Now, first of all, what you should notice is that the mass is directly related to the period of a mass spring system. So as the mass increases, the period is going to increase. And vice versa for the K value. As you have a stronger spring, it's not going to take as long for it to go through one cycle or one oscillation. And therefore, as the K value goes up, the period actually goes down. Those are inversely related. But with a simple pendulum, what we'll notice is that if you have a longer pendulum, it takes more time to complete a cycle, which makes sense. Think about a pendulum this long versus a pendulum this long. The time it's going to take to make a cycle here might be pretty quick, whereas here, you're traveling a much further distance. So just think about it physically. The distance is like the part of the circumference that you're looking at, that arc length there, and that arc length is much longer in the second situation. So it's got to take more time to cover that distance there. So the length of the pendulum is directly related to the period. But the gravitational constant on the planet is indirectly related. So if we were on Jupiter, where gravity is much higher, if we increase gravity, it's going to decrease our period. Well, gravity's higher, it just means that the object's going to be accelerated faster downward. So if it's going faster, it's going to complete that cycle much quicker on Jupiter compared to the Earth. Or something like the Moon, where gravity is only a sixth that of the Earth, it's going to end up being a period that is much longer because it moves slower. And you can see that whenever you see those comics of like people jumping on the Moon, they're moving very slow because the gravitational acceleration there is much less than that of Earth. We should also be able to solve for these variables as well through the process, being able to solve for M or K or L or G, and we'll see that in one of our examples here. One of the most important and interesting things to notice is that the period of a pendulum is independent of the mass. So the mass of the actual bob at the end of the pendulum has no effect on the period, which is a little bit misleading because you would think that if the object was larger, it would like pull down faster. But if we remember that all objects fall at equal rates on Earth, assuming, air resistance being negligible, then we could see that it's the gravitational constant that really does affect it, but not the actual mass. So we could have an object here that's made of wood, and then take another object in the same exact height and, make believe it's made out of metal. The mass could be 10 times that of the other mass, but the period will still be the same. Example 1 says a mass of 20 kilograms is connected to a spring and it oscillates in simple harmonic motion. If the spring constant is 35 newtons per meter, then determine the period and the frequency of this system. So for a problem like this right away, we're going to be looking for period and frequency. Well, we have the mass as 20 kilograms. We've got the spring constant of 35 newtons per meter. And if we remember that period equals 2 pi square root of m over k, we can find our period using the mass and the spring constant. So let's go ahead and plug those in. We get period equals 2 pi times the square root of m over k, so we have 20 kilograms over 35 newtons per meter. And what we'll see is that we'll have some cancellation here because newtons are really kilograms meters per second squared. That'll leave us with seconds squared underneath the radical. But since we're taking the square root of that number, our units also become just seconds from seconds squared because the square root of something squared is indeed itself. So we end up getting here, when we plug in these numbers, a value of 4.75 seconds. Now, if we know that the period is 4.75 seconds, we could just do 1 over that to give us the frequency of the oscillations. Again, frequency equals 1 over tau, which is 1 over 4.75 seconds. And we'll see that our units are 1 over seconds, which is what we were talking about earlier. That's what a hertz is. So hertz are the units, and it's 0.211 hertz. And this answer is logical because if we think about it, the reciprocal of a number like 5 is 1/5, which is around 0.2. And since this number is around 5, this should be around 0.2. Alright, in this problem now, it says to determine the length needed for a simple pendulum to have a frequency of 2 hertz. Well, we're given the frequency, so omega is 2 hertz right away. But the issue we have now is that the length of a pendulum is related to the period of the pendulum with our formula tau equals 2 pi square root L over G. And we'll notice that there is no omega in this formula. Well, there's two options. Either option 1, you can find the period just by doing the inverse, again, like we said earlier, so this would be just 0.5 seconds, the inverse of 2. Or you could simply take tau and plug in 1 over omega in its place. Here, you can put a 1 over omega there and solve for L. It doesn't matter either way. I'm going to solve for L in the first case up here. So let's go ahead and solve for L. So let's bring this down here now. But if we did it the other way and we just plugged in omega at the end and solved that way, it's the same, but it's easier to solve in the first case, so I choose the easier direction here. So let's divide by 2 pi first, giving us radical L over G. Then we'll go ahead and square both sides of the equation. Tau over 2 pi, that whole quantity squared, equals L over G. and then multiply by g on both sides to get L by itself. That cancels this g right here. So the length equals g times the quantity tau over 2 pi squared. Now we're going to go ahead and plug in the numbers. Well, we know what g is. We're on Earth, so that's 9.81 meters per second squared. Tau is 0.5 seconds all over 2 pi. That quantity squared equals the length, giving us a length of a pendulum of 0.062 meters. Well, let's write that in centimeters so we can make sense of this answer. That's 6.2 centimeters. If you had solved by using omega, the answer you'd get would be the same, but the generic solution that you have up here would be different because you would have used omega. If you had done that, this is what it would have looked like solving generically using omega in there. You would have g, parentheses, 1 over 2 pi omega squared equals the length. Had you solved with omega in the formula, but since we used tau in the formula, we got this generic solution up here instead. Example 3 says, if the length of a simple pendulum is increased by a factor of 4, what happens to the period of oscillations when it is set in simple harmonic motion? So we want to think about what happens to our actual period here. Okay, what happens to the period? Well, the period equals 2 pi radical L over G. Well, now we've got a period of a new pendulum. We have to figure out how it changes when we have 4 times the length. Well, that's the only difference there. This 4 right here. And if you remember your laws of radicals, if we have a product underneath a radical, we can break that product up. So radical 4L is the same thing as radical 4 times radical L. So in essence, what this becomes is the following. 2 pi radical 4 radical L over G there. So I'm taking that radical 4 and moving it out, which is fine just because we're factoring it there. And then the radical 4, square root of 4, that's really just 2. So in the end, this equals, this 2 pi is still here, and the L over G is still here. So I'll write those together, just so we can compare them. But then there's also the number 2 in the front here. I'm going to move this radical 4 out front, just to show me that, here's the old period, here's the new period. It's the same thing at first. These are identical except for this 2 in the front. So our period of the pendulum has increased by a factor of 2. And what we can see here is that this happens because L is underneath the radical. Since L is under the radical and the length increases by a factor of 4, the period increases by the square root of that factor. So if we wanted to generalize, we could say that as L increases by some factor, the period of oscillations increases by the square root of that factor. The square root of that factor. And this is analogous to a mass spring system. If we had 2 pi root m over k, okay, if you change the mass, the same thing is going to occur. If say you increase the mass by a factor of 7, well, that's going to increase the period by a factor of the square root of 7, because the mass is underneath this square root up here. The constant g and k would be inversely related there. So if you increase the factor k, the spring constant, say you made it a spring that was triple the strength, so you increased it by a factor of 3, you'd be decreasing the period by a factor of square root 3, again because it's under the radical. Example 4 says, a mattress is really a surface that rests on a multitude of springs. Imagine that there are 200 springs inside of the mattress, even though there really are many more. If a person lying on it has a mass of 70 kilograms, then determine the spring constant of a single spring if the simple harmonic vibration immediately after the person lies down has a period of 1.5 seconds. And that makes sense. If you've ever laid down in a bed or sat in a bed, it takes like about a second or so for the bed to stop. It kind of bounces for a second there. So about a second and a half for the period of oscillations. So let's write down what we know. We know that there's really 200 springs inside of this, but the mass of the person is 70 kilograms. Let's assume, even though it's not really true, that the 70 kilograms is evenly distributed to each spring. So each spring feels a mass of not 70 kilograms, but 70 kilograms over 200. So that gives me exactly 0.35 kilograms of mass per spring. Now again, if you're laying on a bed, your body is not evenly distributed on the bed really, so you're not going to be spread out on all 200 springs, but we're modeling this with a little simplicity. Next, we'll notice that we have the period being 1.5 seconds, and we want to find out what the actual spring constant is for one of those springs. So we can go ahead and solve. We got tau equals 2 pi root m over k. Well, now it looks like we're going to be solving for something in the denominator of a radical. So let's go through this process. We'll divide by 2 pi to start. and that equals root m over k now. We'll square both sides, giving us the quantity tau over 2 pi squared equals m over k. And now since we're looking for k, think of this as v equals x over t. How would you? And the way you would solve this would be to switch the v and the t here. We've seen that many times. You could solve for t. So take this k and switch it with this entire expression here. Again, we're just multiplying both sides by k and dividing by the quantity tau over 2 pi squared all at the same time. Okay, now we're just going to plug in. The mass is 0.35 kilograms all over the period of 1.5 seconds over 2 pi, that whole quantity squared. Now remember to put parentheses around your entire denominator, or it's not going to come out to be the right answer, but you'll get a K value of 6.14 newtons per meter. So that means it would take 6.14 newtons to stretch these or compress these springs a distance of 1 meter, even though they wouldn't really go a distance of 1 meter because they're not even that long. We could really convert that to centimeters if we wanted to, and we could say, well, you know, this is just going to be 0.0614 newtons of force to stretch it 1 centimeter.